In this lecture, we are going to talk about half-lives. Now, a half-life is the amount of time required for the concentration of a reactant to fall to half of its initial value. So it goes from 100% to 50%, or from 50 molar to 25 molar. And that amount of time is used to track the length of a reaction or the amount of time a reaction is taking and compare between different reactions because the concentration changes at a different rate as the reaction progresses. So it's easiest to track this through half-lives. And so we see that our half-lives are going to be order dependent. If a reaction is zero, first or second order, we'll see a different type of half-life. Some will be dependent on the initial concentration that we have of our reactant, and some won't. So we'll walk through those now. Right here, I have a graphical representation of an actual first order reaction. And so in this one, we see that the half-life is independent of the amount that you start with. And so no matter what you start with, after the same amount of time, so one half-life will get you to half of what you had initially. And after a second half-life, you'll have half of what you had after that first one was over. And it'll kind of keep going in halves. It kind of reminds me of Zeno's paradox, where, I can walk towards the table and get halfway there, and then I can go half the distance and then half the distance, and I'll never actually arrive at the table. But eventually we will just have like two molecules left and then one, and then we can't have half a molecule. So um, let's take a look at these based on order. So here's just a quick summary for zero order reactions. So remember, these are not dependent on the initial amount of concentration that we start with for the rate. However, the amount of time that then is in a half-life will depend on that initial concentration. And so we see that that half-life is whatever amount you start with divided by 2 times the rate constant. In our first order, then we have actually a half-life that isn't dependent on concentration at all, which is interesting. It's 1/2 T1/2 is equal to 0.693 divided by the constant for the rate constant. Sorry, and that's because if we're looking at concentration being divided by 2, right? Our initial concentration will be twice that of our final concentration for the interval of time that would be our half-life. And so we can think of this piece right here as being like, oh, well, let's say I have 100 molar initially, and I'll be tracking how much time it takes to get to half of that, 50 molar. And so no matter, since I'm always looking at what my concentration at T is always going to be half of it initially, I'm always going to end up with the natural log of 1 divided by 2. And that's going to equal that 0.693. And then after that, I'm just dividing by K. And so all of these half-lives are just developed by having our concentration at time T equal 1/2 of the concentration that we have initially, and plugging in a value of like 1 and 2 for our concentration at time T and our concentration initially throughout our integrated rate laws. And that's how we're getting to these T1/2 equations and solving for T. So for our second order, we are going to once again depend on initial concentration. And we'll see for second order reactions that half-life is going to be the inverse of the rate constant times the initial concentration that you start with for your reactant. And so these are kind of handy to have with you when you're studying. If you ever forget it, or you feel like, you can always derive it just by remembering that our concentration is just 50% of what it was before, and using that to solve for the T1/2 equation. And what we see as this sample decreases by half is that after the first half-life, we'll have half of what we started with. So that's what we're showing right here. And after that second half-life, we'll have half of that half. So we'll have 1/4 of what we had initially. After that third half-life, we'll have 1/8. And this will keep going. We'll keep going by halves. It'll decrease to 50%, then 25%, then 12.5, then 6.25, then 3.125, and so on. And so we can capture that after the nth T1 half, our concentration is going to be the initial amount we started with divided by 2 to the power of n. So that would mean we could interpret this after the fifth half-life. The concentration is going to be equal to our initial concentration divided by 2 to the power of 5. And so we can figure it out that way and substitute in for whatever half-life we are calculating out to. And here is a summary. This is so you have it in your notes all together. It's also in your textbook. Hopefully, this one's out of a different textbook. I liked it a lot, though. It just shows everything you need for zero, first, and second order. So we have rate laws and the units of your rate law constant, the integrated rate law, what the straight line plot would be if you were evaluating experimental data, and also the half-life expression. And so this is kind of a nice, handy, consolidated version of rate laws to keep handy when you're doing homework and things like that. Let's walk through an example with that real quick. So iodine 132 undergoes a first order decay, and it has a K value of 0.302 hours. How much time will pass before iridium 132 decays to 12.5% of its original amount? So the first order is really helpful. We know then that our half-life is going to be equal to, here we go. Let me write this out. Our half-life is going to be equal to that 0.693 divided by our K value. So I can go ahead and just plug that value in and find out what the half-life is going to be. So our half-life is going to be 2.295 hours. So that's the first part of this, but now we need to know how many half-lives would pass. And so this 12.5% is the key to it. And there's a few ways to solve this problem. If you do it differently, that's fine. So I'll just show you one tactic. So the 12.5% is really 0.125, right? So that is going to be the concentration that our reactant will be at relative to our first one. So thinking about this in terms of our concentration at time t is equal to that initial concentration divided by 2 to the n will tell us the number of half-lives. We're really looking for then 0.125, that's our 12.5%. That's going to be equal to 1 over 2 to the n, where n will be the number of half-lives that pass. So I'm going to go ahead and just solve for that. So I'm going to rearrange this equation. So I have 1 over 0.125 is equal to 2 to the n. And this is going to equal 8. So then I'm going to have 8 is equal to 2 to the power of n. I'm going to take the log of both sides. So log 8 equals n log 2, and n is equal to log 8 divided by log 2, which is equal to 3. Therefore, I've got 3 half-lives that pass. All right, so 3 half-lives are going to pass to hit 12.5% of the original amount. I know my half-life is 2.295 hours. So after 3 half-lives, the amount of time that passes is just going to be 3 half-lives times the amount of time, 2.295 hours, like this. So if I wanted to write that out, inverse hours, hours. If I wanted to write that out kind of in a dimensional analysis style, I guess what I could do is write, so 3 half-lives times 2.295 hours per half-life. And that equals, so those half-lives cancel out. And that's going to equal 6.885 hours, or 6.89 hours.